Okay, let's start. First of all, I would like to thank the organizers for the nice possibility to present here my work. This is a joint work with Professor Kotlarov. And we consider the modified Korteweg-de-Vries equation, and we are interested in the long-time asymptotic behavior of its solution. The initial data is supposed to be a step-like function that tends to a positive constant c when x tends to minus infinity, and tends to 0 when x tends to plus infinity. And mostly we are interested in the following domain. The line x is equal to 4c squared t is called the leading edge. And we see that this domain is very close to the leading edge. So we see that this domain is a small domain which is close to the leading edge. If epsilon is a small positive number, then we see that the left border of this interval becomes very close to the leading edge. It means that the right border is even closer to it. But because of different choice of parameterization, we have logarithm t in the right border instead of t in the left. We can say that the right border, we can distinguish a non-small parameter n in the right border, and hence in some sense the right border is better separated from the leading edge than the left border, which is farther from it. We need to make some assumptions. First of all, we assume that the solution of this initial value problem exists, and for every time it tends to background constants c and 0 with the first moment, so that the following integral inequality holds for all values of time. It gives us possibility to use the machinery of direct transform problem for some associated lex pair operator. So we have your solutions, the reflection coefficient, transmission coefficient. Also, we suppose that the initial profile just at one point, at the point t is equal to 0, tends to this background constants c and 0 exponentially fast in the following sense. And this gives us a possibility to extend analytically the reflection coefficient from the real line into the upper half plane. Also, we assume the absence of usual solitons. That means that the inverse of the transmission coefficient doesn't vanish in the upper half plane. And I said that we are interested in the asymptotics in this region, and this is true, but unfortunately we don't know how to study asymptotics there. All that we know the asymptotics in the adjacent regions, from above and from below. And this gives us opportunity to say something also about this region. Namely, it allows to make some negative conclusions about what cannot happen in this region. The asymptotics in the domain above this region was studied by Khruslov and Kotlarov using the method which was introduced for the Korteweg-de-Vries equation by Khruslov. In its turn, this paper by Khruslov was motivated by the previous work of Gurevich and Pitaevsky, who showed that for step-like Korteweg-de-Vries equation, there must be a train of some soliton-like, there must be some oscillations which are gathering, which are concentrated in the vicinity of the leading edge. So, in this domain, the asymptotics for Q has the following form. We see that these terms look very similar to the solitons. And the only difference is in this logarithmic term. Without this term, this expression would, term in this expression would satisfy the modified Korteweg-de-Vries equation precisely. And with this logarithmic term, this Expressions satisfy the modified Korteweg-de-Vries equation with some error, which tends to 0 as t tends to infinity. And hence they called these objects asymptotic solitons. We can notice that the influence of the initial profile, of the explicit form of the initial profile, is relatively small here. Довольно малое влияние. Relatively small here. It is presented only in this constant phase alpha and tilde. And alpha and tilde is determined via the transmission coefficient in the following form. Here we have a coefficient h star, and it is presented and it determines this coefficient alpha and tilde. So we see that the contribution of the initial profile is relatively small comparing to the input from the background constant c, which is clearly presented in this formula. In this phase, alpha and tilde will play important role in our daily discussion, in our further discussion. We see that in particular, if we assume the absence of solitons, of usual solitons, in general they can be presented and they run in front of the leading edge. Their velocity must be bigger than 4c square. But in our case, the solution tends to 0 in front of the leading edge, and everything interesting happens in this small logarithmic domain below the leading edge. We see that each asymptotic soliton has a center on the following line, on the following logarithmic line. So again, we see that choice of parametrization is a good choice of parametrization. And each n describes here a new soliton. And the asymptotics below that small region which we are interested in was studied by using the Riemann-Hilbert approach, and the main term of asymptotics is described in terms of the following modulated elliptic function. Here the parameter d is determined from the following system of equations together with the quantity mu, and the parameters b, delta and tau are determined by using these parameters d and mu by the following formulas. And again, we see that the influence of the exact form of initial profile is presented here only in this parameter delta via the transmission coefficient. And everything else in this formula is determined only by the background constant c. So again, we see that the influence of this exact form of initial background is relatively insignificant for us. This is just to say something about this formula, just to describe it in some way. We will not use this fact anywhere. We see that when t tends to infinity, then this term t multiplied by b tends to infinity, and hence it leads to these oscillations because theta function is 2pi periodic function, while this term delta is just a constant along every line where x over t is a constant. Since that region which is described by this small parameter epsilon is quite small, and since this left border is relatively close to the leading edge, and we have this elliptic asymptotics up to this left border, we can ask ourselves whether the modulated elliptic asymptotics is still valid in the remaining domain up to the leading order, up to the leading edge. It turned out that this q elliptic, that this elliptic wave, has the following asymptotics in this small logarithmic domain. We see here expressions which are very close to what we have seen just several slides ago for Q. We have exactly the same domain, exactly the same logarithmic domain. We have slightly different error term. Here we have t to minus 1/2 instead of t to minus 1/2 plus sigma, which we had before. But this is not very important. And the main difference is in this phase alpha n of xt. Imagine for a moment that the phases would also coincide with the previous phase. It would mean that this elliptic asymptotics also valid in this small logarithmic domain and up to the order term of t to minus 1/2 or t to minus 1/2 plus sigma. And since this elliptic asymptotics is valid up to the line 40 squared t minus epsilon t, and in this small logarithmic domain, most probably it would also mean that in the remaining part, the asymptotics is also described by this elliptic wave. But it turned out that the situation is more interesting, and these phases, they do not coincide. Let us call these objects by elliptic asymptotic solitons to distinguish them with that true asymptotic solitons. First of all, we see that each soliton is centralized along the following logarithmic curve. Yes, and also we need to say some words about this function alpha n of xt. The explicit expression for this function is quite cumbersome, so we will not write it down here. But what is important for us is that this function alpha n of xt is almost a constant, is just a constant in the Lydian order if we consider our xt on the following logarithmic curve, which is parameterized by some coefficient gamma. And this alpha n of xt in the Lydian order is determined only by this coefficient gamma. It is equal to some alpha n of gamma, which has the following form. Okay, so we see that along the logarithmic curve, this alpha n of xt is almost a constant. And also we see that this soliton is centralized along such, is supported only in the small vicinity of such a logarithmic curve. So we can ask ourselves a question. Maybe we can change here alpha n of xt with some constant. If yes, this constant would definitely be alpha n of xt, which is calculated along the center line, so that we calculate alpha n of xt at the point on that logarithmic curve, which is parameterized by gamma, where we take gamma to be equal to 2n minus 1/2. But it turned out that the rate of vanishing of these solitons is not fast enough to change this variable phase to a constant. In that, if we consider a logarithmic curve in the vicinity of the center line, which has some difference, which is expressed by parameter epsilon logarithm t, then the soliton will be of the order t to minus epsilon on this line, multiplied by some constant. Soliton with a constant phase will also be of the same order t to minus epsilon, but multiplied by a different constant. Here we calculate it at the point 2n minus 1/2 minus epsilon, and here we calculated it at the point 2n minus 1/2, and these are different constants. So the difference from these two solitons will also be of the order t to minus epsilon, which is bigger than the biggest admissible error of the order t to minus epsilon. And so we can conclude that these phases, they do not coincide on the central. Yes, so we can conclude that Yes, and also, moreover, we see that these phases, they do not coincide, or these phases. So we can conclude that elliptic asymptotics doesn't describe the asymptotics, that the elliptic wave doesn't describe the asymptotics on this logarithmic neighborhood of the leading edge. But we can notice an interesting thing, that despite these phases, they do not coincide in that. They do not coincide because the expression for alpha n is the following expression, and the expression for alpha n tilde has the following form. So we have two completely different expressions. But it turns out that when n tends to infinity, consistently with t tends to infinity, so that the following expression tends to 0, then the phases became closer and closer to each other. And this suggests a hypothesis that q elliptic and q are close to each other for both n and large and t large. But how this mechanism occurs, we don't know. This is unknown for us. Now I would like to describe briefly Hruslov's methods for finding asymptotic solitons, then method for finding modulated elliptic asymptotics, and how to decompose elliptic wave into a train uh, of soliton-like terms in the vicinity of the leading edge. So actually, Kotlarov and Hruslov in their paper they considered much more general situation when the initial profile tends to a finite gap potential. So our case of constant background is a simple particular case of their work. They are based on the Gelfand-Levitan-Marchenko equations, which for modified Korteweg-de Vries equation has the form is a system of two equations, because the Lex pair for modified Korteweg-de Vries equation is a matrix pair, is a matrix Lex pair. The kernel H of xt here is a integration of so the kernel H of xt is determined here, is defined here by the following formula. So we integrate the reflection coefficient multiplied by some exponential over the continuous spectrum, and then the solution of the modified Korteweg-de Vries equation is reconstructed from the functions k1 and k2 in the following way. Yes, and these equations for k1 and k2 are we are looking for them as functions of z, and we consider x and t as parameters. Okay, let us notice that if we are in front of the leading edge, then the kernel h, all the exponentials here okay, so we just mentioned that when we are in front of the leading edge, then the kernel is close to 0. We can see this from this expression, and hence the solution of this system k1 and k2 are also close to 0, and also that's why q is also close to 0. Let me make some changes in my notes. Okay, so then they make, to study asymptotics, they make a change of variables, which centralize everything in the vicinity of the leading edge. So they subtract 40 squared t. Then they noticed that the main input to the kernel comes from integrating over a small interval in the vicinities of the point IC. Then they write the exponential here as a partial sum, prove that the residual, that the income from the residual is negligible, and they got a system of degenerate Volterra equations, which they can find in the following, the solution of which they could find in the following form. The expression which they got for the solution Q in this way is expressed in terms of the ratio of some determinants of degree of growing degree n. And then they do a lot of technical analysis to present it in the form of sum of asymptotic solitons, which we saw before. So I'm also making some changes here. Okay, so now let us consider the method for finding elliptic wave. It comes from the following Riemann-Heber problem. So we are looking for a 2 times 2 matrix valued function, which is analytic in the complex plane without the following counter, sigma, which is depicted in this picture. Here the quantity d, delta, and b, they were already defined before. R of k here is a reflection coefficient, and the function f capital and f hat and g are determined in the following form. So we see that the function g is determined just by the background constant c. So we don't see here the influence of the initial profile, which is important to determine the functions f capital and f small, which are determined. The function f capital is determined from the following conjugation problem, from the following scalar conjugation problem. And then we notice that the main input to the asymptotics okay, so we notice that for fixed d, that is when we are far from the leading edge, then the main input comes only from the interval from on the imaginary axis from IC to minus IC, and because the jumps on another lines is close to identity matrix. And this gives us a model problem which can be solved explicitly in terms of elliptic functions, and this gives us this elliptic asymptotics of the following form. Okay, and finally, let us concern expansion of this elliptic wave in the vicinity of the leading edge into soliton-like expressions. I just would like briefly say some words about difficulties or some key places which we have there. So first of all, the series which represent theta functions, they became slowly convergent when we approach the leading edge, because this parameter tau, which is a b period of the corresponding Riemann surface, tends to 0. To overcome this difficulty, we use the Poisson summation formula, which rewrite slowly convergent theta series into fast convergent theta series. So here we have parameter 1 over tau. So if tau tends to 0, then the parameter 1 over tau tends to minus infinity, and these series become very well convergent. Then we rewrite the expression for Q elliptic in the following way, in the following form, and then notice that since in each theta function here is represented by some fast convergence series, so the main input to each series comes maximum from 2 or 3 terms, and then we can rewrite this ratio in the following form of inverse of hyperbolic cosine. And for short, we denoted here by z the following expression. Okay, so we already have the correct structure of this expression. Yes, so we have sum of inverse of cosine hyperbolics, and now we need to reorganize the argument in this cosine and we need to reorganize this argument. We need to find its asymptotics, and when we find this asymptotics, actually it has the following form. So we got our elliptic solitons, which we saw before. We need to introduce here small parameters in order to write this expression, in order to express this term in terms of x and t. We need to find asymptotics of a number of integrals. We need to study asymptotics of a number of integrals. Some of them are calculated straightforward, and for the other we need to use some tricks. For example, to calculate asymptotics for the integral I0, it is enough to make change of variable, to convert the shrinking interval from d to c to a constant interval from 0 to 1. Then we take asymptotics of the integrand, integrate it, and we got the asymptotics for the integral. But it is another matter with the integral of I1, because here when d tends to c, we just got divergent integral. And to find the asymptotics of this integral, we use the following trick. We have an interesting identity in theta functions which connect b period tau, this coefficient, how to say, b period in theta functions, which connect this tau with this geometrical object d. And rewriting this theta series into fast convergence series, we have got relations between tau and d, or here it is written in terms of a small parameter eta, which is associated with d. Okay, now come back to this formula. We see in this formula we already know the asymptotics of the integral I0, and we already know the asymptotics of tau star in terms of d when d tends to c. So this gives us the asymptotics for the integral I1, and we have it in the following form. So we have in that it's growing and can be expressed in terms of this logarithm. Then we calculate a number of other integrals in the following way, and find the asymptotics of this this argument in terms of the parameter d. And now we need to rewrite it in terms of the physical parameters x and t. And the link between d and xt is given by the following formula, which is the first equation which determines d and mu. And it is interesting to notice that here we have a Lambert equation, and after inverting it, after finding a solution of it, we can express the argument in terms of the variables x and t, and see the formula which we saw before. Okay, so в главном это все. Here is the literature. So the first paper is the paper by Hruslov, where he introduced his method for finding asymptotic solitons in the vicinity of the leading edge. In the second paper, Hruslov and Kotlerov found these solitons for the modified Korteweg-de Vries equation in a much more wider setting. So they considered finite gap backgrounds for the initial data. In the third paper, we found the elliptic asymptotics, and in the last paper, we studied the relations between this elliptic wave and the asymptotic solitons. That's all. Thank you very much for your attention.